Okay, so what did we talk about last time? Last time we talked about like floating base, 3D kinematics-y stuff. We did this stuff, kind of the, there's some more stuff in there that you can worry about. We only did prismatic joints pretty much, right? I suppose you could do other joints with that setup too, but like we kind of didn't talk about prismatic joints there. Revolute, we did revolute and not prismatic and stuff. There's other things that you can do in there, but hopefully that was enough to like sort of give you tape and be dangerous. And then we did like sort of the floating base 3D dynamics in 3D, right, in joint coordinates specifically, which is kind of the standard thing that pretty much everyone does, and that's most common in the robotic simulators. It's definitely most common in control, and it's also probably, kind of arguably the most common thing in simulators. This is what Bullet, Dart, and Rujoko all do, this setup, right? We have a floating base and you have a bunch of joint angles for all the other things on your robot. So typically, right, you'd have like you'd treat like, say, if you have a legged robot or something, you'd have the torso be like your floating base, and then all the limbs would be joint angles, parameterization, right? This kind of thing. So that's one way to do it. Arguably the most common way, kind of the standard way in most of the control stuff and simulation stuff. Today we're going to talk about, so we kind of got into this at the end of last lecture based on like from a question from Jacob. And so today we're going to like tell that story in a more complete way. So this isn't the only option basically, right? So we talked about like generalized coordinates. You can pick any coordinates you want, blah, blah, blah. Most popular in robotics, probably the so-called joint coordinates, which are, if it's a fixed base, those are minimal. In the floating base context, if you use a quaternion, it's not minimal, but they're sort of almost minimal, right? The other option, or an other option, is so-called maximal coordinates, which is what we're going to talk about today. What has an interesting history that like, and has some interesting trade-offs versus the like joint space stuff. And let's see. And then what we're going to do today is we're going to talk about that. And then for reasons that I'll get into in a minute, we're going to focus on the variation. So last time, right, we did like the continuous time classical stuff. I didn't actually get to the example. I'll show you the example from yesterday or last time today. And basically there, we did it in continuous time. It's like, manipulator dynamic stuff, and you use your normal like Runge-Kutta stuff or whatever to simulate that, right? So it turns out in maximal coordinates, that setup doesn't work super well. We talked about this a little bit earlier in the class. We talked about Baumgart stabilization. You guys remember this, where you kind of like put PD controllers in to make sure your constraints stay satisfied and all this weird stuff. So for this reason, like the maximal coordinate stuff in continuous time isn't very good. It requires all this stabilization stuff, and you can end up in situations where like your robot will like drift apart, and you're like, your arm will start floating out of the shoulder joint and stuff like this because of this constraint drift phenomena that happens in continuous time. And then you have to add this stabilization stuff, and that makes the equation stiff. And then your Runge-Kutta method doesn't like you anymore and has to take tiny steps, and bad things ensue. So for that reason, it's not great. And that's the main reason it's less popular in robotics, I would argue. But as the theme of the class would suggest, basically all of the badness associated with this goes away in the variational integrator setup, because it like automatically satisfies all the constraints, symmetries, blah, 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 like we keep seeing over and over again. So it turns out maximal coordinates in the variational integrator setup just works automatically, and it's pretty good. So we'll talk about that today, and I'll sort of show you how that works. But you can do it in continuous time, modulo those caveats. And, it's not particularly hard to do. And I'll kind of explain it, and you should be able to figure it out from the discussion today. But we're going to focus on the variational integrator story. Sort of, we did the previous stuff was all continuous time. If you wanted to do the variational integrator setup there, you know what to do. You take the Lagrangian and turn a crank through all the stuff we've talked about before, right? Okay, same story here. You should be able to figure it out. So let's talk about what this whole maximal coordinate story is about. So who's heard of this before, or played around with it, or whatever? Okay. Not too many. Okay, so like I've been saying, sort of the joint coordinates setup are kind of the standard thing in robotics for the most part. But they have some trade-offs that aren't all good. So the conventional reasons for this choice that you'll hear people talk about are the following. So first off, no constraint drift issues. And then the other one you'll hear is they have a smaller state vector, right? Like a more compact representation. And you'll hear maybe people talk about how that's good for computational reasons or something like this. But I would argue that's a very naive perspective that's missing the boat. So that's what people will tell you. The first one's, again, true if you do it in continuous time with a classical Runge-Kutta thing. The second one isn't really a thing. Because we'll talk about maybe after Thanksgiving, these whole like, the linear time algorithms, Featherstone stuff. Basically, that stuff you can do in either setup. And that has more to do with the topology of the system and the sparsity structure and stuff like that. That sparsity structure shows up in either setup. And in fact, it's easier to see it in maximal coordinates. So if you're smart about the problem structure, these things actually are computationally the same, and the size of the state vector makes no difference. Okay, so that one's sort of not legit. Let's see. Yeah, with careful implementation, computational cost of these guys is the same. We're going to do this after the break. Okay, let's see. And then, yeah, the variational integrator setup gets rid of the constraint drift issue. So maybe this isn't such a bad setup. The other, so the big win for maximal coordinates is, one, it's super easy to do and it's super modular. So like it's very easy to set up and simulate complex things with it, which we'll get into. The other big win with maximal coordinates is you basically never have to do forward or inverse kinematics again, because everything's just there, right? Like forward kinematics, the whole point of that is to get like the full world frame, like SE3 pose of all your links by sort of traversing and going and like, taking all the joint angle stuff and doing it. So if in maximal coordinates, that's your state vector, right? The full SE3 pose is just in the state vector for everything. So you basically never have to do these forward or inverse kinematics again, which is kind of nice. And it turns out to be a big win in a lot of contexts. It makes some things a lot easier. So I would argue like the maximal coordinate setup is just easier to deal with and like easier to do complicated things with, and eliminates a lot of the pain points that you have with the classical stuff, the joint coordinate stuff. But you have to do fancier integration stuff and be clever about the implementation to make it work well, to make it basically to get rid of those issues, right? So the basic idea here is really simple. It's a really, really dumb, simple idea. Literally all you're doing is taking the Newton-Euler dynamics for each link, like as in floating base, free rigid body, the stuff we talked about, right? The SE3 stuff, quad rotor stuff, whatever. You just do that for every single link. And then you just write down joint constraints explicitly. And you get a giant set of Newton-Euler dynamics and joint constraints. So when I say modular, it's trivial to like modify the robot setup, add more links, tweak stuff. It's super nice computationally because it's this very modular plug and play setup versus joint space where you've got to like worry about, if I change the robot somewhere, I've got to now like rework all my kinematics. It's a big thing, right? So that's very, very nice. And things are just like super clean, I would argue. So we already know how to do Newton-Euler and we already know how to do constraints, right? So this is going to be a pretty straightforward story. And I would argue the main story here is how to implement it efficiently. Because if you do it naively, you get large problems, right? Because you've got a huge state vector now with all these constraints. The trick is to like harness the sparsity structure and do this linear time stuff. Cool. And then, yeah, we're going to focus on the variational integrator story, because really that's the only context in which this maximal coordinate stuff is sort of worth doing. So I guess my sidebar take on this is if I were building a simulator now, I would do it this way. I think it's a much cleaner setup. If I had to like build a full up robot simulator, which my lab did over the last couple of years. And you know, this is how we did it. So there's good reasons to do it this way. Okay, so the big thing we need to do this is, so we're gonna do the variational integrator thing. You already know how to do that. You already know how to do constraints in there. The big thing we're missing for this is Newton-Euler dynamics in discrete time. You know how to do the Newton part, right? We did like particles and stuff. The thing we didn't do yet, which was on the homework, so lots of hints today, is the Euler part. So we got to do the rigid body attitude dynamics stuff in the variational integrator setup. So if you already did this on the homework, you already kind of know what's going to come up today. Hopefully we'll fill in any holes in there. But it's kind of not a surprise what's going to happen. So we'll kind of go kind of fast through this. So discrete time. And just like in continuous time, you can decouple the position dynamics from the attitude dynamics, and you get a F equals ma part and a like, you know, Euler's equation attitude dynamics part. So we're going to basically focus today on the attitude dynamics part and show you how to do that with like our quaternion tricks. So let's just summarize real quick the other part. So translation stuff is easy. We're going to get our Lagrangian. The Lagrangian for the whole thing, right, includes both of these things. If remember, we talked about how they separate out and there's no cross coupling between translation and rotation. So we're going to kind of just write the translation part. Where they could be coupled is in the potential, but usually they're not. So then you get your discrete Lagrangian thing where we just take this and like integrate it rectangle rule style over a time step. So we just like take this guy, evaluate it at the midpoint, and multiply by an h. So this is all stuff we've seen before, just like refreshing our memories. Midpoint, blah, blah, blah. And then we plug this into the discrete Euler-Lagrange equation thing that looks like this. Oh, this is a -1. And remember, we're going to sort of like do this again for the attitude case. But basically what you do is we derive this a few different ways, right? And the simplest way, the Zach way, is to write down the discrete action sum over just 3 knot points. And then endpoints are fixed. All you got to do is take the gradient with respect to the middle knot point, right? And then this equation pops out. You can also do the index gymnastics thing where you write down the whole sum and do that like weird integration by parts index manipulation trick, which we also did. That's like the classic way, but we're going to do it the Zach way today because it's easier. Okay, cool. And then, yeah, just like as a yeah, we're going to just like, I'm going to just state it right. We also did external forces and constraints and all that stuff in this setup. So I'm just going to write that down. So like control inputs, right? All that kind of stuff. They just get kind of tacked on in the expected ways, you know, just like it was a sort of manipulator equation type deal. So you get this kind of thing again. So this is like your Euler-Lagrange stuff or your manipulator stuff. And then you get your like external forcing term, which we're going to use a midpoint approximation. So that's going to look like this. So this is like TK minus 1 plus H over 2. And then you're going to get a like another one of those if we're doing midpoint. So remember, this is like 3 time steps, right? We have QK minus 1. Gotta make my indices. So QK minus 1, QK plus 1, right? And so these get evaluated like the midpoint of each of those. So this guy's like this midpoint, and then the next one we get at the next midpoint. So this is like this midpoint, right? And then we get our constraint term, which looks like this. So this is our constraint equation. That's like our constraint. So this is like your, okay, so this is your constraint term. And then these guys are your forcing terms. And then you also, right, you're going to also have to satisfy the constraint equation at time k plus 1. So the idea is we're enforcing this. We already know QK minus 1 and QK. We only have to, we're solving for QK plus 1. We want to enforce the constraints at k plus 1, right? So this setup, these are a bunch of nonlinear things. We solve this with Newton's method by plugging in QK minus 1, blah, 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 and solve for QK plus 1. This whole like, yeah. Oh, sorry. Yeah, I meant T. It's just whatever the force is at that time.
And is one of those a minus?
They're both plus. I mean, you could write this different ways. So this is my indices are not legible.
Is that a TK?
That's a TK minus 1.
Oh, yes.
So what they're just the midpoints of these intervals, right? So one goes with this guy, one goes with this guy. And then, so that's sort of, I'm like second order accurate midpoint. The constraint though, technically this is basically like an Euler, you know, sort of thing. Here I'm like 0 order holding the constraint force over the time step, just evaluating it like on the knot point, whatever. There's more to say about this. So this guy's only first order accurate technically. I think I talked about this a little bit when we did this the first time around. So the sort of one big deal here is, unlike the continuous time f equals ma version of this, where we do constraints, right? There we have to double diff the constraints, and we get this like thing that's in terms of acceleration, and that's how we get drift, right? In discrete time, we're explicitly solving for QK plus 1, the next pose, right? And so my joint constraints here, if I satisfy this at time k plus 1, I satisfy the joint constraints exactly. I have to solve this with Newton's method to do it, but like if I solve this thing, that's it. Like the joint constraints are always satisfied exactly, right? So that's a nice thing. Okay, cool. So this we've seen before, and then this is just straight up translation. This is really, really simple, right? It's literally like the f equals ma thing with your position constraints and whatever your external forces are on the body. Now we need to do the same thing for the Euler part, right? The attitude part. So that's what we're going to do now. Okay, so what we're going to do is just do the unforced case. This is actually a lot easier than the mess we did last time, where we did like the attitude dynamics in continuous time. Turns out this is a lot simpler, which is cool. So I'm basically going to just do the unforced case. So like the discrete Euler Lagrange thing. The forcing and like constraint terms look exactly the same. So I'm just going to like quote them. They're not a big deal. If you want to derive them, you can do it. It's not hard. You'll have the tools. So here we go. Okay, so our Lagrangian, like we did before, is this guy, where you got your inertia and your angular velocity. And the big, like the only real trick here that you need, there's like weird quaternion stuff that's going to happen, right? And we talked about how if I just naively plug this in, you don't get the like cross term, the Coriolis term, right? So you have to be smart about the quaternion stuff. Basically, there's 2 key tricks here. One is not a surprise. Like basically, you have to like do the quaternion attitude Jacobian derivative stuff when you take the derivatives, which we'll see, not a big deal. The other one is how you get this omega. So we're gonna just like in the position version, we're gonna use poses, right? And so what we are gonna need to do is finite diff quaternions to get a finite diff omega approximation, right? And like up here, we just subtract and divide by a time step, and that's all good, right? But I can't do that for the quaternions, right? Like subtracting them is sort of not legal, blah, blah, blah. So we're gonna do it a slightly different way. So there's a couple ways to think about this. I'm gonna write it, maybe I'll just like write this down one way and we'll talk about it a little bit. If I like, I know you guys kind of played with this. If I like, you know, put a gun to your head and told you you had to do this, like, how would you do it? If I gave you like a pair of quaternions or whatever, or a time series of quaternions, and I was like, give me like finite diff these and give me omega. Like, what would you do? Yeah, so that's exactly right. That's like the legit thing to do. So what we're going to do is essentially that, but we're going to play an extra approximation trick because we're going to derive like a first or second order-ish integrator. So we're going to basically tailor expand that log term to like first order and just take that. And that's good enough for us. It turns out you get the same answer, and it's a little slightly computationally cheaper because you don't have to actually evaluate a log, and it's just algebraic. So that's what's going to happen. You can derive this in a couple ways. I'll write it down. So this is what we're doing. So this is totally analogous to the position version, but like you got to diff it a particular way. So I'm going to write it, we're going to write it a little bit differently, which I think is more analogous to the way it's on the homework, but it is what you just said also. So here's like another way of getting at this. So here's my quaternion kinematics in continuous time, right? So if I were to like do an Euler approximation of this thing and like integrate this over a time step, I get something like the following. Right. Everyone cool with that? So I literally just did QK plus, you know, little h times what's this thing, right? And if I like kind of massage this around, I can write this as QK plus, or QK times an identity quaternion plus this like hat thing. Does everyone get how I do that? This is QK plus QK times this guy, right? So I'm just gonna do QK times like identity plus this guy. I'm pulling that out. That makes sense to everybody. And then I can write this as just L of QK times this guy. So let's talk about this. Does anyone recognize like this thing? Yeah, sort of axis angle-y thing. So this is like that phi guy, right? Omega integrated over a little L H. But remember what you said, right? This whole log thing. So what's the exact solution to this? If I have a constant omega over the time step, I zero or hold omega of this guy. If I integrate this over a little h exactly for a constant omega. What kind of ODE is this in omega? Looks like x dot equals stuff times x, basically, right? It's a linear first order ODE. The exact solution to this, if I have a constant omega, is the exponential, right? It's e to the, you know, this guy h, right? Okay, so with that in mind, the answer to this, the exact answer is the quaternion exponential, just like the matrix exponential. So what's this thing? Like, think about this. What is this? It's the first order Taylor expansion of the exponential. So we're just basically all we're doing here is the exact solution to this. If I want to have, if I have an axis angle, is to like do the exponential thing. This is a first order Taylor approximation of the exponential. And the argument here is that like I don't care about the higher order terms because they don't affect my answer in the integrator at all. That's like what's going on. And then I'm just going to take this and solve it for omega. So my finite diff approximation looks like this. And then this is what you said, basically, right? So I'm going to basically do the, the Q dagger Q thing. This is like the delta Q, right? And then what I'm literally doing here is just taking the vector part out of that instead of taking the log. Oh yeah, you're right. Yep. So this is literally doing like QK dagger, QK plus 1. It's giving me the delta Q. And then this guy's picking out the vector part. Just that's it, right? And turns out that's, obviously, based on this argument, that's the first order Taylor expansion of the log. Okay, so everyone get like that story? Yeah.
The first one, when you do the QK plus 1, and then like the what, like is equal to QK plus H of like Q dot.
Yeah.
Is that like, is there a reason we could do that like with quaternion thing?
So like this is like sketchy.
Yeah.
What this is really is this whole thing, like this is one way to think about it as like a dumb Euler step. The right way probably to think about this is the exact solution to this is the exponential. This is just first order Taylor expansion of the exponential. Is that sort of,
Yep.
Yeah. And then the reason we can kind of get away with this is like so for finite omega, this is not a unit quaternion, right? Yeah. And like that actually jives. Like if I do only a first or second order Taylor expansion of the exponential, I'm actually not guaranteed to get a unit thing, right? It's only if I take the series out really far that it'll converge to like the unit answer. The reason we can get away with this and that I still preserve the unit norm and stuff is because after this, I actually just pick out the 3 vector and that's it, right? So like all the unit, now once I've done this, the unit norm constraint, isn't a thing anymore, right? So does that make sense?
Yeah.
Cool. Okay, hopefully that's sort of okay with everyone. But yeah, the right way to think about it is really like, I would argue like, this is just first order Taylor expansion of the exponential, which is the correct, like exact thing, right? And then if I invert that, the first order Taylor expansion of the log. And this is all we need basically for like our first order integrator or whatever. Okay, hopefully that's okay with everybody. So that's like basically this is centered finite difference of quaternions is what this is, right? And if you wanted to be like super legit about it, you would take a log, but in the limit of small h, small time steps, this is very accurate. That's essentially, if you took bigger and bigger time steps and this got bigger, if this delta Q is big, then this first order Taylor expansion of the log is maybe less good, right? And you might want to like think about some other, higher order version of this or use the actual logarithm. But it turns out, yeah, for our purposes, not going to matter. And as long as you're taking fast enough time steps in your integrator, this approximation is fine. Okay, cool. So now we're gonna write
Sorry,
out.
I want to jump in here on this.
Yeah, go for it.
So this doesn't work on the homework. Like this doesn't pass like the unit tests. So I don't think this is like what's happening.
We should go look at the homework together then.
No, this works. This passes the unit test.
Okay.
You might have put it in right. I will also mention that if you did kind of like a naive thing, like what I realized that I did on my homework, and just plop in the midpoint approximations for Q dot and Q. This exact equation also pops out. So if you did that, that'll also pass the unit test. So probably if you were implementing that, you might have just put it in the wrong place or something. But yeah, this will work.
Basically, yeah, the whole thing about subtraction versus multiplication, like this is kind of what I was saying on Slack. The difference basically goes away under this first order Taylor approximation. Like you can kind of think about it either way. But
Sure.
yeah, it's totally possible that I'll take another look if you want to chat after.
Yeah, I'll play with it more.
Show me just show me what you're doing, and maybe we can like figure it out. It's totally possible there's a mistake in the homework code as well. So I would be curious to try it and check it out. But yeah, this is how I did it. So if I like, it's totally possible I screwed something up in the homework, but I think this works. So definitely the math works this way. The code might have a screw up in it, so we should tag up after and double
Cool.
check. Okay, cool. So this is not, I mean, this is the attitude Jacobian thing right here. You don't have to do that yet. That's really like, we talk about that in the context of like diffing stuff. We're going to use it right now. So what we're going to do now is just write the discrete Lagrangian thing. So that's trick number one that you need, is how to finite diff the quaternions. And again, there's multiple ways to do that. This is the dumbest, cheapest way. There are other more accurate ways, but this is all we need for like a low order integrator. And then here's sort of the discrete Lagrangian thing is exactly what you expect. I'm just going to take the continuous time one up here. I'm going to plug in this finite diff omega approximation. I'm going to multiply by an h. So this is what you end up getting. It's like QK dagger times QK plus 1. And I can write this in terms of like the, you know, the L's and whatnot, the attitude Jacobian stuff, which we're going to do in a sec. I'm just going to write this out this way because I think it's a little clearer to see what's going on. By the way, can anyone tell me how did we decide on like the ordering of this? Like, why is it QK dagger times QK plus 1 and not the other way around? What if it was QK plus 1 times QK dagger, whatever? Sign, that's kind of, yeah, sort of. Can anyone tell me what the difference would be if I like swap the order there? What would I get? So this is like the delta rotation between the two time steps, right? So it's an omega thing. You can think of it a couple ways. If I do it this way, I get omega in the body frame. If I do it the other way, I'll get omega expressed in the inertial frame. And that'd be kind of interesting to work out for yourselves. That's like a thing, right? Like there's some ambiguity there. I could imagine doing this in either order. In like the position case, it kind of doesn't matter. But here it matters which order I do these things in. Okay, cool. So that's it. We do this, and then we're just going to write down the action sum thing over a couple time steps, like we did before. And we're going to minimize this like discrete action guy with respect to the midpoint. So this looks like min over Q2 of this discrete Lagrangian thing. And again, I'm only going to write it down over the minimum possible number of time steps, which is 3 knot points, or like, you know, 2 of these little discrete Lagrangian guys. And we did this in the position case before, right? So here, again, the argument is this whole thing, like the hanging chain, whatever, I keep the endpoints fixed and I minimize with respect to like, you know, stuff in between. And that whole like dynamic programming self-similarity argument, I can do this over like a tiny segment, and it has to hold true for the whole thing. So I'm going to just take the smallest segment I can possibly take. And I only have to minimize with respect to one midpoint guy. And I'm just going to do like again, this is stupid simple. I literally am just taking the derivative of the Q2 and then slapping on that attitude Jacobian to like impedance match us back to 3D derivatives. So that looks like this. I'm taking the derivative with respect to Q2 of this guy, and then I multiply by the attitude Jacobian evaluated at Q2. And then I do derivative with respect to Q2 of this guy. And I slap on the attitude Jacobian here with respect to Q2 again. This whole thing has to equal 0. These guys are the attitude Jacobian things. Okay, that's it. Wasn't that nice? So much nicer. That's all you got to do. Beautiful. And then you do Newton on this with the quaternion tricks, right? Like that we talked about. That was on the homework 0 question, but that's it. And then like, this is the free one with no forcing, right? Adding the forces and stuff, the external torques, whatever, and stuff, and the constraints to this is easy. It looks the same as the other case. So we're not going to do the details, but I'm going to just quote it. This is obviously on the falling brick because you need to add in the constraint forces, right? You know, I was thinking about, so like, you know, the continuous time version of this was so ugly and like, honestly, it's awful to derive. This is so clean. Like, and I've been trying to find a way to do this in continuous time, like this cleanly. But I think actually the right move is probably to just do this first and then take a limit of this as h goes to 0 to like derive the continuous version. That's like actually how I should do it next time, is do it this way first. Anyway. Okay, so this looks like, I'm going to write this out in detail, which is a little gross. I'm going to plug in like all the attitude Jacobian nonsense, right? So it's going to look, and I'm going to expand out these guys. So I'm going to actually like just expand this. It's going to look ugly, but it's just the LDs getting expanded out. So here's what it is. This looks pretty gross. But again, not actually. Oh, you know what I just realized? I overloaded L. I've got like Lagrangian and left multiply. That's super annoying. Apologies. Hopefully you can tell. Okay, so here's your, constraint thing. And you take the normal gradient and then you slap on the attitude Jacobian stuff. Actually, I'm going to write this down or next row. So none of this is a surprise. So that's your discrete Euler-Lagrange stuff. This whole thing is just this stuff, right? And what I did was basically pull the G's out and like combine stuff and whatever. That's not hard to get. I just plugged in the definitions for LD. The next term is your constraint Jacobian with an attitude Jacobian tacked on. So that looks the same as the position case, right? It's just got this extra, did I do this right? It's got a lambda K on it. And then I've got my external forcing term, which looks exactly the same. Got some torques here. Oh, right. I'm like sort of evaluating things at 1s, 2s, and 3s and not Ks and stuff. So make sure I do this right. So this is the same as the other stuff. Here, there's no attitude Jacobian stuff because this is actually just 3D torque. So that's fine. Okay, this whole thing equals 0 and the constraint equation at the last, next time step equals 0. Okay, so these guys, this is the constraint term. And this is the torques. External torques, right? Cool. Looks a little messier, but yeah, it's really clean. Like this is it. And then this stuff is the same as before. You just get this attitude Jacobian tacked on here. It otherwise looks the same, right? So I think pretty straightforward. Any questions about this?
The first line of that, should the Q3 at the end be a G of Q3?
I have to think about this. So the G is there, that H transpose L transpose thing.
Oh, I see. Yeah.
I just like expanded it out in all the gory detail.
Why doesn't Q1 show up in that?
Did I screw? Oh, that should be a Q2. Sorry. Wait, I think I've messed up some indexing. Let me like double check this real quick. This should be Q2. Oh, I totally dropped stuff. Sorry, I messed up. Sorry, say that again. I think I just screwed up. Give me 1 sec to like check my math. This is G of Q2. Yeah, I messed up. I'm actually gonna have to like fix this whole thing, I think. It'll be easier. Okay, what did I do here? So this should be the following thing. G transpose Q2 L of Q1 H J H transpose L transpose Q1 Q2, and then that's the first term. Then this is the second term. I like how to. This is ugly and like whatever, just lots of bookkeeping. I don't think there's anything, you know. Okay, so that's it. So this is your like DEL stuff. And then you've got the constrained terms of torque term. That's just expanded out from the line above by plugging in all of the, you know, the definitions of the omega Ks and like the expanding out that whole thing. Does that make sense, Jacob?
Yeah, that looks, yeah, that makes sense.
Okay. Thanks for catching me. Okay, cool. So then like all you do is stack this with the translation equations and all your constraints, and then you just solve it all with Newton. Well, links and joints. Okay, so what we're going to do now is I'm going to do an example where we set up like a floating, it's really like a floating double pendulum. It's a double pendulum that's like, or floating acrobat or something might be the right way to think about it. So it's like two links with a single pin joint in between them, and I can apply a torque at the joint. So basically it's like a little, I don't know, two-link floating acrobat that I can wiggle around. So that's it. I'm going to show it to you using the stuff from last time, and then this stuff kind of side by side so we can look. So I'm just going to briefly show you how to what this thing looks like. So it looks like this. It's got a link, a joint, a link. And we've got like a CG, you know, and I'm going to define these like vectors here from like the CG to the joint on both of these guys like we talked about. So this guy will be B1, and then this guy will be A2. And then this guy's got position R1, attitude Q1, and, you know, likewise over here. Okay, so how do I write down the joint constraint for this guy? So there's kind of two pieces. There's the position piece that just says these 2 points have to lie in the same inertial position. And then there's an attitude constraint as well, because I'm going to make this a revolute joint that can only rotate about one axis, right? And we're in 3D, so I have to constrain away, you know, bending in this direction and twisting in this direction. So those are the two things I got to do. So let's write down the position one first. That one's easy. So I just say R1, which is the inertial position of link one, plus, you know, like a forward kinematics type thing from the CG of this guy from R1 to the joint. So that's going to look like this. I'm going to rotate it into the, I'm got to rotate this thing into the, from the body frame into the inertial frame and add it on. So it's just the rotation matrix version of Q1 applied to the vector. And if you remember, we did this like a while ago. The rotation matrix in terms of the quaternion looks like this. I'm just going to write it out. So that guy times the B1. So it's literally just this guy's in the inertial frame. This guy's defined in the body frame. I rotated in the inertial frame and added on, and that gives me the joint location in the world frame. And now I'm gonna do the exact same one on the other link. So it's R2 So I'm gonna write down what the constraint looks like. So I'm subtracting these guys from each other and setting that to 0, right? So everything's a minus sign over here, same deal, just apply to the other link. So this is Q2 and this is A2. And this thing has to equal 0, right? And okay, so that's that. So that's the position part. And then the attitude part, what do you guys think we would do? What would you do if I asked you to like write down constrain out the other 2 rotation degrees of freedom? How would you think about this? Actually, a bunch of ways you could do it. Any thoughts? Yeah. So. And then what? Okay, so what you're talking about doing is actually like straight up converting it to like a joint angle thing or something, and then setting those equal. That's a very messy way to do it. Yep. So it's 1 degree of freedom, and you're just trying to constrain out this one and this one. Right. So I want to remove, so I have 2 degrees of freedom to remove, right? How do I do that? So I want to set some stuff equal to 0, right? So the easiest way I know to do it, there are like many ways. This most straightforward way, in my opinion, would be to take like the Q1 dagger Q2 thing and get this delta Q between the joints. And then all you have to do is set their X and Y. So it depends how I define this. If I define this to be like the body Z axis or whatever, then I'm just got to set the delta Q's X and Y components equal to 0. That's the constraint, right? And for a quaternion, that's actually easy because inside there is basically this like axis angle-y thing, right? So I just pick out the X, Y components from that axis angle thing, set them equal to 0. So that's it. That makes sense. And so actually for arbitrary axes, you can also do this. You just have to like grab the correct component out of there, right? Do like a projection of the axis angle onto the joint axes, joint axes you want. Okay, so that's what we're going to do. There are other ways to do it. So we're going to assume this is the body Z, which it's arbitrary. Again, this makes it easy though. Again, this is in the link frame. Okay, so we're going to do this is, so we'll call this like a delta Q, and this is Q1 dagger times Q2. And remember, this is like an axis angle type thing. So it looks like this. I don't know what this is annoying. Gotta come up with like a axis-y thing. So I don't know, like we'll do this. Trying to not overload notation. I already used like R and A for other things. So and yeah, the way to think about this, right, is I'm doing Q2 equals Q1 times a delta Q. So this delta Q is therefore defined in the like relative to Q1, right? In the Q1 prime. You can do it either way. The upshot is if it's the Z-axis, you know, that I'm rotating about, the Z-axis is the same in both frames, right? Since it's pinned. So that's why it does this one. Actually, I could do it either way and it wouldn't matter, right? What that would effectively mean is I'm either putting the delta Q in the Q1 or the Q2 frame, but because it's a pin joint like this and the Z-axis has got to be the same in both frames, I can write it either way. Oops. Okay, cool. So that, so then this is easy. I got this guy. All I'm gonna do is look at this guy, which is like a weird, nonlinear scale version of the axis angle vector. I'm just gonna put it, pick out the X, Y components of that guy and say those have to be 0. Okay, so that's what we're doing. The vector part of Q. So we just get this little Jacobian thing here that's going to pick out X and Y components of the vector part of that guy. And here's the delta rotation in matrix notation. There you go. So there's your constraint. Now you just stack everything up. Solve with Newton. Okay, now we're going to do it. Any questions about anything? So yeah, like the whole deal is you can write all this stuff in terms of quaternions. This is that C of Q, whatever now. But I've got to play the quaternion tricks because I remember when I do this, I've got to solve that roof finite problem in the quaternions and the position. So when I do Newton, the homework is question 0, whatever thing, I've got to diff this using the attitude Jacobian tricks and stuff like that, right? Inside the Newton solver, but modular that, it's like the thing you expect. Okay, cool. Let's see how to do it with some code. So let's do, I got 2 versions of this. This is the version from last time that I didn't do. Oh, please work. What are you doing? Why are you gonna screw with me? Come on, you stupid bastard. I hate you. Okay. Let's see. What is actually happening now? Like, I can't click this. What is? Okay. This is not cooperating. See, I got it set up and everything before class and it just doesn't work. Why doesn't it work? It works over here. This is interesting. Okay. I can't click on it when it's on this display. This is actually bizarre. I can't click on it on this screen, but I can click on it on the screen on my laptop. Hopefully the keyboard still works. No, nothing works when it's on this screen. That's truly bizarre. If I drag it over here, I can click through and everything works. If I drag it over here onto the other display, nothing works. What the hell? I honestly don't know what is going on here. This makes no sense. Okay, so I can't scroll. Oh, I can scroll, but I can't click, and the keyboard doesn't work either. What the hell is going on with this thing? Absolutely bizarre. I hate computers. No, like there's no iPad. Okay, now it works. Fun. Anyway, okay, so now it's working. Cool. So this is the joint coordinate version that we did last time in continuous time, which is representative of like what Mujoko and Bullet and stuff do, right? Like this is the stuff from last time, bunch of quaternion stuff. Here's the kinematics function. We did this last time, right? So for kinematics-y stuff, I have the base position quaternion, and then I have one joint angle representing this like revolute joint. And this is just me doing that like A and B thing from the revolute joint to write down like the full pose of the second link in inertial coordinates. Kinematic Jacobian, I'm literally diffing this guy and using the attitude Jacobian trick. Mass matrix in joint space. let's see if let me like write it down, and then check its eigenvalues to make sure it's positive definite. So you can see clearly it's symmetric and positive definite. That checks out. That's good. Potential, do I have no potential here because I'm floating in space. No gravity, nothing. Here's my Lagrangian. That's easy stuff. This is Lagrangian derivative. So I'm writing out the derivative with respect to the position and the quaternion, and then the joint angles, right? And then the velocities, omega, blah, blah, blah. This is the stuff we did last time, right? Remember I wrote the weirdo Euler-Lagrange equations down sort of separately blockwise according to like position, quaternion, and then joint angles, et cetera. So this is all those pieces from the last lecture. And then this is the input Jacobian. So this is just showing I have one torque at the revolute joint. So that's that, right? It's in the Q1 spot. Made up initial conditions. This is just floating in space still. And then this is the Euler-Lagrange stuff that we derived last time. So this is messy. But remember, basically what I had, right? I had pieces that were separated out for like the position, the quaternion, and the omega and stuff. So this thing up here, this is the mass matrix, right? This is the thing I'm inverting. This is the derivative with respect to like all the dot things. And then these are basically the potential terms. You see the attitude Jacobian things showing up in here and whatever. But these are exactly what we wrote down in class last time. And this is how you actually implement it. Cool. Warning, this is gonna be slow, extremely slow. And it's because I'm like, I have a ton of these 4 diff calls and they're nested inside each other to get like second derivatives. So it's painfully slow. But this is just vanilla RK4 on those dynamics at 20 Hertz. I'm going to apply torque to the joint, which is like a square wave. So it's going to just wiggle back and forth. Nothing surprising. I'm just doing vanilla RK4. This is the dumb hacky thing that like you would probably do if you were to implement this yourself. So you take an RK4 step and then you just renormalize the quaternion at the end of each RK4 step, which we kind of did before. It was like a easy hacky way of doing this. Very slow again because of the lots of forward diff. And then we can look at the plots. It's already plotted, so I guess we don't really have to wait for that. So what is this? This is like the position, quaternion, joint angle. So you can see it's basically wiggling back and forth. These are velocities, okay, whatever. And yeah, here you can see this kind of like square wavy thing that I was doing, right? Okay, so here's some fun. Let's watch it. Let's do the visualizer thing. Oh, this is now gonna take a while because it's got to wait for the integrator to finish. That's annoying. I'll just do this. It's going to take super, super long time. Shouldn't be too bad. But yeah, it's unsurprising. It's the wiggle back and forth thing. Well, that thing, let's talk about one other little fun thing in here. So this thing's floating in space. I'm only applying an internal torque, right, at the joint. I'm not applying any external forces and torques, right? So there's all kinds of conserved quantities in this problem, right? Like momentum, blah, 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 energy. One of the conserved things is the center of mass position for the whole system, right? I'm not applying any external pushes on this thing, only internally between links. So I take oh, here we go. It wiggles back and forth, yay. Okay, nothing surprising or very exciting about this. Cool, okay. So, but all I'm doing is this, right? So the center mass of the whole system can't move, right? Because I'm not applying any external forces to the whole thing. So just out of curiosity, like I'm going to evaluate this, right? So here's position of link 1, position of link 2, taken from the kinematics, right? So I evaluate the kinematics at t0 and at the end of the trajectory after running the sim. I do the kinematics on those things and I get the positions of both links, right? So at the beginning, the center mass position is exactly like half a meter to the right. And that's because I put the left link at the I put link 1 at the origin, right? So I'm translating over. So it's really, this is the position of the joint, right? So it's half a meter. Cool. I'm going to run the sim and I'm going to evaluate it again. And this is just for fun, right? Pretty good. Like good to like, you know, I don't know, what, 6-ish decimal places, something like that. 5, 6 decimal places. Cool. This is just, I don't know, as an aside. We're going to like look at what this does in the other case. Okay, so cool. That's how you do that. That's how probably just about every robot simulator works. Now we're going to do it the way we just talked about. And wow, yeah, the clicking doesn't work again. Let's see if it works if I do this. It's truly bizarre. I run into like so many stupid bugs in this class, like live in lecture just for you. It's good times. Okay, so this is the same stuff so far. This is all the same. We're gonna do like 20 hertz again. Here's all the quaternion stuff that we use. Now this is that discrete Euler Lagrange stuff stacked up. So this is the position stuff. This is just, 1/2 mv squared type stuff. And then this is the attitude stuff that we just wrote down, right? And this is for link 1, link 2. That's exactly what's in the notes, right? Okay, so that's that. Then I'm just writing down the derivatives. So this is like the derivative with respect to Q3. If I have Q1, Q2, Q3, lambda, and this is the forces, right? So I'm just writing down that derivative. You get the attitude Jacobian shown up, right? Here's the constraint that we talked about. So it's literally, this is like the rotation part that we derived, and this is the position part up here, right, that we just wrote down. So that's the joint constraint. This is the derivative of the constraint. I'm just using forward diff and being lazy, and then tacking the attitude Jacobian on, right? Easy. Initial conditions, same as last time. It's just like sitting there, not moving. And then this is the same force as last time. I'm basically putting in like square wave, stuff. So one thing to note, right, is like I'm applying this at the joint. So applying forces is a little weirder in this context, right? So I don't have like a coordinate in there for the joint. So I got to do that like virtual work thing, right? And get that like coordinate, the matching Jacobian thing. In this case, I'm going from like the force, the generalized force is expressed in joint coordinates, right? It's expressed on the joint. So I have to do the like Jacobian that maps us from that into these maximal coordinates, right? That's basically what's going on here. So here's the torques are just square wave, kind of things applied on the joint. And then this guy maps us into the joint space, the maximal coordinates. And what's going on here, right, is this is, XYZ position, and then XYZ, so XYZ force, XYZ torque, right, on the two bodies. And what I'm getting here is torque on link 1, torque on link 2, they're like equal and opposite, right? So that's what's happening. That's why it shows up like that. You could define this, you could do the virtual work thing and get a Jacobian, but it would basically be this, like, okay, cool. So now we're gonna do the simulation. What's in here? So this is our big loop. We're doing the Newton thing. This is the Newton method on the discrete Euler Lagrange stuff with the attitude tricks for the quaternion. What's in here? So this is that like derivative with respect to Q3. And then this is the constraint stuff, right? And I'm solving simultaneously for the, I'm doing root finding on Q3 and lambda. I'm solving for lambda as well, right? So this is basically all that stuff. Yeah, this is like I don't know, you guys did this already, / we've talked about it. It's in the homework, so hopefully this is not, if anyone has questions, speak up, otherwise we'll keep trucking. This is just doing the Newton tricks with the attitude, Newton with attitude tricks. Now we're going to do the visualizer thing again, and this is not super exciting. It should look, visually exactly the same as the last one. And then for fun, we're going to go do that, like evaluate the center of mass of the whole system again, right? This is at T0 and this is at T at the end. And you can see, so, okay, that's exact. This one to numerical machine precision preserves that like, center mass position out to like whatever 15 decimal places or whatever, because it does all the nice things, blah, blah, blah. Variational integrators are cool. Okay, cool. So that's that. So this is, yeah, like this example code in particular, like is, what you need for the homework question with the falling brick with this stuff pretty much / these notes. So if you haven't done it yet, there you go. If you did it already, good job. I'm proud of you. Okay. Anybody have any questions about anything? All right, then. I think we are done for the day in that case. And I'll hang out for a little bit. If anyone has any burning questions or homework issues or whatever,